New Good afternoon, everybody, and Happy New Year. Okay, you get that? So this is the beginning of 2026, and we're gonna start the year with Sudaruti, but I'm gonna introduce you in a second. We have a list of speakers, some of them coming from UC Davis colleagues here on campus, some of them speaking from outside via Zoom. So it's very exciting. And we also have some of you students presenting this quarter, although most of you will be presenting in the spring. Okay, I think we have one or two openings, but everything else is filled.
For this quarter, one.
For this quarter, just one, the one in March, right?
Yeah.
Do people have access to the list of speakers?
They should, but I can also send it out.
Yeah, we can send so people know what is coming. So we were struggling a little bit with the venue. For obvious reasons, Young Hall is not the most welcoming place. So I want all of you to think about it, how you think this place is right now. On Tuesday, when Philippe taught, it was very noisy and it was very dirty, right? Philippe, you had to clean. It was not noisy, it was not very dirty. Yeah, I saw you with cleaning supplies. So, okay, you should put that on your service. So think about that. When we send the poll, not most people, but the majority of people chose Young Hall. So that's we wanted to respect. But we can revisit that. So if you have some questions or comments, please let me know. Let me know. Good. Okay, so Sudaruti Baral, I think everybody knows him. He is a second-year student from Kolkata originally. He did his undergraduate work at UNC Chapel Hill, with a double major in statistics and in psychology. And he's been working with us ever since. I would describe Sudaruti as a very shy, quiet, introverted individual. One of the things that I enjoy working with Sudaruti is his enthusiasm and his curiosity. And I always think about the nature of learning and the nature of a student to be curious. So I think that's a wonderful trait. As an example, it was last year that I sent, I think, to all of you a talk that was happening in the stats department about functional data analysis. And Sudaruti and Rocky, you went as well, right? Went to see the talk, and about a week or two weeks later, Sudaruti said, you have an idea for a project. But you have never heard of functional data analysis. And in a matter of some time working with Jonathan and working with me, you put together a paper that is now under review in Site Methods, and you're going to be talking about this. So I was very impressed by that. Let's see the reviewers are as well. That is beyond our control. But that was an example of independence of thinking, creativity of thinking, and taking initiative. And without further ado, just see that it's
Thank you for the incredible kind words. It would not have been possible without the mentorship of both of them. Okay, so let's get started. The topic is, today I'm going to talk about a non-parametric approach to modeling accelerated longitudinal designs. So this is the overview. So I'm going to start by talking a bit about the history of both accelerated longitudinal designs and functional data analysis. Then I'm going to talk about how we are extending the model in question, and then how we are comparing the functional data model to some of the traditional models in psychology. Finally, we are going to end up with an empirical illustration and some concluding remarks. Okay, so let's start with the historical overview of accidental longitudinal designs. Now, when we are studying anything in developmental psychology or anything over long time spans, we might want to learn about this underlying latent trajectory of a specific individual. But if we actually want to study that, we might have to collect enormous amount of data, and that's very resource intensive. Instead of doing that, we can do something like this. We can collect small snippets of longitudinal sequences, and with certain assumptions of ergodicity, we can capture the entire latent trajectory and the entire process. There have been quite a few papers that have used ALDs. Some of them are listed here. There are some various statistical models that have been used to model ALD. Some of them are here. One of my favorites is this model by McCardle called the latent growth curve, named the growth model of competing forces, where he would use two different parametric models, one to talk about growth and one about decline. And it's a very nice name. You might also be familiar with the latent chain score model, and we're going to talk more about these models in today's talk. Traditionally, they were developed in discrete time. More recently, continuous time models have been developed to extend this. But the thing is, both the continuous time and the discrete time versions impose strong parametric assumptions and structural assumptions as well. Now, what do I mean by that? Let's look at this classic paper by McCardle. Here he used 7 different parametric models to analyze growth and decline of various psychological constructs. When I say that these parametric models impose strong structural assumptions, what I mean is that all individuals are sort of forced to follow this specific trajectory, this specific population trajectory. Now, do we actually believe that all of them are following the same functional trajectory? Maybe not. Maybe some follow a different trajectory. Maybe some decline faster than others. It's difficult to capture that using a parametric model that imposes some structural assumptions. I'm going to go back a little bit to this paper by Ledyard Tucker from 1966, where he was exploring various learning curves. And he used singular value decomposition to basically analyze various forms of and modes of learning. You can look more into the paper. It's a very nice paper, but I'm going to specifically focus on this group. And his conclusion was that when he used exploratory techniques like SVD on such learning curves, he found not just 2, but 3 learning curves. At that time, it was already well known that some people follow an exponential decay function, and some others follow a sigmoidal function. This factor B was pretty novel back then. And his claim was that the fact that till then people would only think of learning behavior as belonging to an exponential decay function or sigmoidal function was in a sense limiting. Instead, if you use some exploratory approaches, you can figure out or explore some other newer learning curves, and that gives us a better understanding of variability in learning in human beings. So there seems to be a necessity of going away from parametric models to non-parametric models to explore different functional forms in our data. Speaking of functions, let's talk about functional data analysis. Like most things in statistics, functional data analysis has been claimed to be started by this guy, Fisher. Recently, functional data analysis celebrated 100 years of the functional linear model. I will say that Fisher was probably not the person who kicked functional data analysis into popularity. It was probably functional principal component analysis that did that. Again, functional PCA also celebrated 50 years in 2024. The idea of functional data analysis is that instead of thinking of data as specific points, we think of the atoms of analysis as functions. Now, these functions are continuous in nature and smooth. Since these functions are continuous, they are necessarily infinite dimensional in nature. And we cannot work with infinite dimensional objects. There seems to be a necessity of dimensional reduction. And that's where functional PCA comes into being. Functional PCA helps us to reduce the dimensions into specific modes, specific functions called eigenfunctions. And that helps us work with functions much easier, which is why I'm claiming that functional PCA is what pushed FDA into popularity. Also, an interesting connection is that functional PCA can be thought of as a continuous time generalization of Tucker's generalized learning curves, because singular value decomposition can be connected to FPCA through the Mercer's theorem. So it seems like a continuous time extension of his idea. Even though there seems to be some connection between psychology and statistics, at least theoretically, not much crosstalk existed for quite some time, until this person came into being, James Ramsey. In 1982, he published this paper in Psychometrica, which got pretty popular. And in fact, his book, Functional Data Analysis, is one of the best written books on functional data analysis. Highly recommend it to anyone who is interested in doing it. However, Ramsey's work solely focused on functions that that came from data that were intensive in nature. Often, we do not work with data that are intensively sampled. Think of your longitudinal data. They are not intensive in nature. We only have 3 or 4 time points per subject. If you do want to do that, you cannot use Ramsey's methods. That's where UC Davis comes into the game. Hans Puller in 2025 developed an algorithm that allowed us to model functions from longitudinal data. And more recently, in 2024, with his postdoc Edom, they used stochastic differential equations to model accelerated longitudinal data. So you can get functions for functions from data points that can be as low as 2 per subject. This seems pretty relevant because what we are going to talk about are accelerated longitudinal designs. So let's talk about FDA SDE a bit. What does this algorithm do? What this algorithm does is that it uses this specific solution to a stochastic differential equation, which has conditional means and conditional variances, and it also uses initial values. If you give this algorithm a specific initial value, it will use local linear regression to estimate the conditional mean and the conditional variance. With the specific initial value, it can estimate unique simulated trajectories that are continuous and smooth in nature. Zhu and Muller established that this algorithm can help us recover the population curves, with the only assumption being that the underlying process is Gaussian in nature. It requires no other assumption. So that seems pretty good. However, this method does have some practical limitations. The first issue is that what this algorithm gives us is a population curve. Often, we might not be interested in just the population. We might be interested in you, or me. And if we are interested in individual subject level trajectories, the population is probably not enough. Moreover, since these trajectories require specific initial values, they did not give us a very good method of getting these initial values. So these two things seem important and need to be explored. The other thing was that Zhu and Muller's paper utilized simulations that from regularly sampled time grids. Often in real ALD situations, we have irregular sampling from the time grids. The other thing was that they used 1,000 simulated trajectories, and that seemed pretty ad hoc. So we want to explore if there's an optimal choice of these number of trajectories. With that, let's extend Zhu and Muller's model for our purposes. First, let's start with the choice of initial values, because that seems important. Because unless we have a specific initial value, we won't be able to estimate a unique simulated trajectory. The idea is pretty simple, which is why I have a cow on a bike. The idea is that since we are interested in estimating initial values, we are going to take the youngest cohort and just calculate the mean and the variance of this cohort. When we have the estimated mean and the variance, we can identify a normal distribution. And once we have the normal distribution, we can simulate as many initial values as we want from this normal distribution. Now, this gives us a solution for the choice of initial values, but we still do not have a way to estimate subject-specific trajectories. Now, how might we do that? First, once we have all the initial values that we want, we can send these initial values and the data to the algorithm, and it just simulates all the trajectories using the algorithm from Zhu and Muller. So it looks something like this. The red lines are the observed data, and the blue continuous lines are the simulated trajectories. Let's take one specific individual, one specific red line. And then we can calculate mean squared errors for all the simulated trajectories for that specific individual. And then we can sort them. It looks something like this. This is for subject 210. Once we have all the MSEs lined up for all the simulated trajectories, we can find the elbow using an algorithm called the needle algorithm. It's a pretty neat algorithm. I'm happy to talk about it more if you're interested. But once we have the elbow, we can take all the trajectories under the elbow, and they look like this. So these are all the simulated trajectories for the optimal subset. Once we have the optimal subset, we can calculate the mean of these trajectories, which is given in dark blue. It seems, at least for subject 210, that the estimated trajectory for this specific individual matches decently well with the true trajectory, which is given in red. But of course, we need to rigorously study this using simulations. And that's exactly what we are going to do. These are the questions that we are going to ask in the simulation study. First, does our subject-specific curve estimation work? Second, does our initialization method work? And third, what is the optimal number of simulated trajectories? Let's start with generating accelerated longitudinal designs. What is the data generating mechanism? Well, we have 250 subject-level trajectories that are generated using an exponential decay function. This is the equation for the exponential decay function with the parameters over here. After all the underlying true trajectories are generated for each individual, we are subsampling it to mimic an axial longitudinal design. And subsampling is done in a manner that each individual gets 2 or 3 observed time points, and there's no missing data at all. The subsampling method is best explained using an example. Say I take Maya here, and I collect data from Maya on the 1st of January 2024. I am not going to bother Maya till the 1st of December 2024. Between 1st of December 2024 and 1st of January 2026, there is a uniform distribution of times when I'm going to bother Maya again with data collection. And this goes on for 2 or 3 tech points. Finally, since we are using the youngest cohort to define the initial distribution, the normal distribution, we are saying that at least 5% of subjects have to be present at t equals 0. So that's the generation of the ALD. And here are the conditions. So for the initialization method, we are going to use the normal method that I explained a bit earlier. And because we have the true underlying trajectories of specific individuals, we have true initial values of those trajectories. So we can compare these 2 methods, the normal and the true. The other question that we are asking is, what's the optimal number of trajectories? So M here is the number of simulated trajectories per subject. M equals 4 means 250 M or 1000 trajectories. This is exactly the one that Su and Muller proposed in their paper. We're going to increase it to M equals 10, which is 2500 trajectories, and M equals 100, which is 250 times 100, and this is supposed to approximate the asymptote. This leads to a total of 6 conditions, and each condition is evaluated over 100 Monte Carlo simulations, iterations. You might ask, why 100? This entire thing takes 1 month to run, that's why. The metrics that we are going to report, so we have MSE and bias. They're pretty standard, so I'm not going to go into details for that. I'm going to talk about integral squared error. This is a standard metric in functional data analysis, but people might not be aware of this, so I'm going to talk a bit about it. This metric is used to assess the recovery of the true latent trajectories per subject. This is calculated using an integral of the true trajectory and the estimated trajectory. So what it essentially does is it calculates the area between the 2 curves. And since these curves are continuous in nature, we are using an integral. But we cannot always calculate integrals analytically, so we are numerically approximating it using the trapezoidal rule. If you are aware of Riemann sums, the trapezoidal rule is sort of a more precise method than Riemann sums. All of these metrics are reported for both subject-specific trajectories that are calculated using the optimal subset and using the method that Su and Muller proposed, that is using all the simulated trajectories, which essentially comes out to saying that each individual's trajectory is essentially the population trajectory. So we do not care about idiosyncrasies of individuals. Now that we have the metrics, let's talk about the results. So we have already talked about these 2 figures. What I have here are box plots for all of the trajectories and an optimal subset of the trajectories. And this is the integral squared error metric, and this is the MSE metric. For one iteration of the M equals 100 and normal initialization case. What I hope that you can take away from this box plot is that the optimal subset method seems to do pretty well and significantly better so compared to the case where you use all the simulated trajectories to estimate individual specific trajectories. That should not be very surprising because, of course, if you just use the population curve metric, the population curve, that does not really take into account specific idiosyncrasies of subject-specific trajectories. So, of course, using an optimal subset to calculate subject-specific metrics would perform better. And over all the Monte Carlo iterations, that's exactly what we see, that the optimal subset method does give us better estimation. The initialization method also seems to work because there does not seem to be any significant differences between using the true initial values and the normal initialization method. Finally, we find that the optimal number of simulated trajectories turns out to be m equals 4, which is 4 times the sample size that you have. And this is exactly what Zhu and Muller proposed in their paper, so that's not very surprising. I do have one slide with the actual tables if you are interested in seeing the exact numbers, but I do not show them here. But if you're interested and do not trust me, I can show them. Now that we have a method that gives us subject-specific trajectories, non-parametrically so, we can compare it to the standard parametric methods that give us the exact same thing with our absolute longitudinal designs. One method that does that is the continuous time latent change code model. The continuous time latent change code model is defined using this state equation and this observation equation. If you solve the state equation, the ordinary differential equation, the solution comes out to be something like this. And typically beta is negative, which turns out to be, the solution comes out to be an exponential decay function. So what this means is that the continuous time latent change code model essentially imposes the fact that all the subjects in our data set have to follow an exponential decay trajectory. Now, since this is estimated in a state space framework, we can estimate it using a common Boosley filter. Additionally, using the Roche-Tang and Strebel smoothing, we can estimate subject-specific trajectories. And this was developed by Martinez-Huertas et al. In 2024. So continuous time latent change code model seems to be the fairest comparison to FDSD because 1, we get subject-specific trajectories, and 2, this is in continuous time. And since functional data analysis is also in continuous time, it seems quite fair to compare these two methods. So in this simulation study, what we are going to answer are, first, we are going to compare the parametric CT-LCS model to our non-parametric FDSD model. We are going to evaluate them on the recovery of the nonlinear developmental trajectories, and we are going to identify conditions where one method succeeds or fails. These are the conditions that we are going to evaluate them on. First, we are varying the number of participants to be 100, 250, and 500, and the number of time points to be 2 or 3. These numbers come from the data set that we are going to eventually analyze. More interestingly, we are looking at 3 different data generating mechanisms. First, the homogeneous case, which is essentially the same standard exponential decay model that I have talked about earlier. The heterogeneous condition uses the same homogeneous model, but with greater variability in the initial values and the final asymptotes. The other condition is the functional heterogeneous condition. The functional heterogeneous condition uses the same homogeneous trajectories, the same exponential decay trajectories for 50% of the individuals. The other 50% of individuals randomly selected follow a trajectory that's functionally different from this exponential decay function. This is supposed to model or imitate the same trajectories that we have seen in Mercader's 2002 paper, where you can see some decay functions, some early decay and decline in cognitive abilities. So here we have a total of 18 conditions, and these are evaluated over 110 Monte Carlo iterations. You might think 110 is odd, and that is true, but I will answer why I'm using 110 eventually. The metrics that I'm reporting are the same as in the first simulation study, so MSE, bias, ISE. The other metric that I'm reporting is the weight of the 95% confidence interval. Now, why this all of a sudden? The reason is that Martinez-Huertas et al. In 2024, they reported that the continuous time states, the CT-LCS model seems to have ballooning confidence intervals, and that seems pretty interesting and seems relevant to investigate and compare with our MTSD method. So we are going to look at the width of the confidence interval. For CT-LCS, this is easily computed since we have the RTS smoothed error covariances for each subject. And once we have the standard errors, it's easy to calculate the weight of the confidence interval. For MTSD, it's not as simple because we do not have analytic standard errors that are available. So we have to approximate it. How am I going to do that? Let's take this specific subject-specific trajectory. This comes from the dataset that we are going to analyze. And let's take a small section of it. So this is going to be the width of the confidence interval for the 81st subject at 14.2 time point. And then we are going to calculate this width at every single time point as well. So that's how we are approximating the width of the confidence interval for FDA SDE. Let's look at the results now. Instead of going straight into the results, let's look at one iteration of one specific condition. So here I have the homogeneous condition with n equals 500 and 3 time points. This is a simulated data set for that specific Monte Carlo iteration. And I am reporting the ISE for FDA and LCS. I think it's pretty clear that FDA SDE seems to estimate the true underlying trajectory of each individual better and more accurately than CT-LCS for this homogeneous condition. We are going to look at 2 specific cases, one that's a typical case and one that is this 47 subject who seems to be very badly estimated by both of the methods. So first, let's look at a typical subject. So this is a typical subject. On the first panel, I have the true trajectory in red, and FDSD and LCS estimated trajectories are overlaid on top of each other. Both of them estimate the true underlying trajectory pretty well. I have the FDSD panel and the CT-LCS panel as well. And as you might have seen earlier, both of them are estimating the true trajectory pretty well. I want to draw your attention to the confidence intervals for both. CT-LCS seems to have that ballooning effect that Martinez-Huertas et al. Reported, and we are seeing exactly that. So we're replicating the result. Their ballooning, the confidence intervals ballooning seems to happen right before the observed data points. For FDSD, there is no specific ballooning that's happening, but there does seem to be a broader confidence interval bounds at points of curvature. This is our subject 47 that was not well estimated by both of the methods. Both of the methods not estimated well, the person well, but they seem to do badly in very specific ways. For FDSDE, it seems like it estimates this person badly because there's some shrinkage towards the population mean curve. For CTLCS, however, it seems like it almost tries extremely hard to fit to the observed data points. So it almost goes out of its way, it departs from its exponential decay trajectory to fit well to the observed values. And it seems to be very confident in its ability to predict these individual specific trajectories. And it seems sort of concerning. Let's go to the heterogeneous condition. So as I had discussed earlier, this is just the homogeneous case, but with more variability in its initial and final values. For the ISE metrics, FDA and CTLCS do not seem to have a big of a difference, at least for this iteration. But over time, over all the iterations, it does seem that CTLCS outperforms FDSD. But let's look at this iteration for a while. I'm going to again look at one typical subject who's decently estimated by both of the methods. And I'm also going to look at subject 480, who seems to be worse estimated by FDA. Let's look at the typical subject. For this, both seem to do decently well as expected. But it's more informative to look at the worst case scenario. For the worst case scenario, FDSD seems to again shrink the subject specific trajectory a lot to the population mean. Again, CTLCS seems to depart from its exponential decay trajectory to almost overfit to the observed data. This means that FDSD learns from all the subjects and it gets information between subjects to estimate these trajectories. So when there's a lot of variability between subjects, it hurts this method. Whereas for CTLCS, since it tries hard to fit to the observed data by almost overfitting it, even though it does badly before it sees the data, it does decently well after it sees it. This means that it's good for predicting the future, but also you should not always trust the MSE and the bias metrics for CTLCS because of this nature of overfitting. Now let's go into the final condition, which is functional heterogeneous. I think most of us would have expected what's going to happen here. Since CTLCS was never really designed to model functional heterogeneity, of course it will perform worse than FDA, which is non-parametric and does not really care about model assumptions. So FDA does perform better than CTLCS. We are again going to look at one specific subject, which I believe is 47. First, we are going to look at a typical subject, though. This typical subject does follow the exponential decay trajectory, which is why CTLCS estimates this subject's trajectory pretty well, because that's what it's supposed to do. For the other subject, it does very poorly, because for this specific subject, it does not follow the exponential decay trajectory. There seems to be some decline towards the end. And FDA does estimate these specific subjects much better than CTLCS, which fails to cover any curvature towards the end and seems pretty darn confident in its wrong conclusions. Now, let's summarize with the results. For the homogeneous and the functional heterogeneous condition, we see that FDSD performs better on the total curve metrics, that is, it estimates the subject-specific curves more accurately overall than CTLCS. MSE and bias do prefer CTLCS, but that seems to be due to overfitting rather than anything else. For the heterogeneous condition, CT-LCS outperforms FD-SD on all metrics. Moreover, FD-SD shows instability with high heterogeneity. In fact, 2 of the 110 data sets fail to converge because of this high level of heterogeneity. And that's why I had 110, because we wanted at least 100 Monte Carlo iterations to have converged. For the impact of sample size and time points, we were observing the exact same thing that you would expect. More number of subjects and more number of time points means better estimation of the subject-specific trajectories. For the width of the 95% confidence interval, we see that CT-LCS does have that ballooning tendency right before it sees the observed time points. So at the earlier ages, there seems to be a lot of ballooning. And for certain cases, the uncertainty might exceed more than 10 to the power 5, and it sometimes even becomes intractable. For FD-SD, the confidence interval widths remain pretty stable, small, and they are also interpretable because they are not blowing up. Also, there seems to be a slight increase at the curve inflection points. That is when the trajectory slows down. And that also seems to be explainable. However, FD-SD's trajectories are empirically estimated and not analytically so. So that seems to be one drawback. Let's end it with a couple of empirical illustrations. The first data set that I have here comes from Jack McArdle's National Growth and Change Study, where he had 672 subjects measured at 2 time points and between ages of 5 and 22. The cognitive domains of interest here are fluid reasoning, crystallized knowledge, academic knowledge, and quantitative ability. And fitting all the data to FD-SD shows us that FD-SD does cover all the subjects' data decently well. And here are 3 specific subjects from the data set. On the top panel, I have FD-SD, and the bottom panel is CT-LCS. For FD-SD, it seems like all the subject-specific trajectories are smooth and they are quite similar to each other and seem decently interpreted. However, for CT-LCS, the first subject that I have here does seem to show the same problems that I have discussed earlier in the simulations. That is, CT-LCS goes up. It seems like it's going to follow the exponential decay function, but then it suddenly drops down to try to fit well to the observed data. And you can see the ballooning effect here as well. So all this is to show that the simulations do carry over to real data sets. For the second empirical illustration, I have the NORA dataset, where we had 95 subjects measured over 2 or 3 time points between ages of 7 and 22. The concept of interest here is fluid reasoning. Since we have a smaller sample size, FD-SD does not seem to do as well in covering the entire real data, but that's fine. More interesting here is, again, the 3 subjects captured at random. Here, I want to draw your attention to the confidence intervals. FD-SD seems to have confidence intervals decently well established because they come from simulated curves, right? However, for CT-LCS, for this subject and this subject, the confidence intervals do not even exist because the covariance matrix becomes singular in nature. So you cannot really compute the confidence intervals here. And that seems problematic again. Final concluding remarks. There are a lot of limitations to this project because this is the first paper that tries to bring in methods from functional data analysis to analyze accelerated longitudinal designs in psychology. As a result, we had to restrict our search space by quite a bit. There can be other data generating processes, sampling designs, missingness patterns, noise levels, growth functions, and whatnot. Our initialization strategy might fail if the youngest cohort is not representative. The linear algorithm might not be the best way to get the optimal subset of trajectories. Finally, since these methods are non-parametric in nature, the interpretation of individual curves might be challenging on a case-by-case basis. Future directions, any of these limitations can grow into a paper in and of itself, but there are some other future directions as well. We can extend comparisons to other parametric models as well. We can apply these methods to broader psychological domains to see if FDSD also works in those domains. We can extend FDSD to include clustering, and more importantly, we can integrate FDSD with certain functional linear models to allow for covariate analysis. And that might help in making these non-parametric methods a bit more interpretable and explainable. Finally, we need to formalize standard errors for FDSD because right now we are just approximating it empirically. And formalizing standard errors seems to be a good next step. But as for conclusions, if you are using FDSD as a non-parametric method to analyze your data, we advise you to use the youngest cohorts distribution to get initial values to start off the algorithm, and use our proposed method to estimate the smooth subject-specific trajectories. CT-LCS, the parametric method, seems to perform better on observed data metrics, but FDSD does better overall for the overall underlying latent trajectory for the subjects. FDSD is recommended when you are doing a bit more of exploratory and descriptive analyses, particularly when you want to detect or even investigate the presence of functional heterogeneity in your data. CT-LCS will never give you that, but CT-LCS is better suited for confirmatory analysis and when you want to test your theory. Finally, this project would never have been possible without my wonderful mentors and co-authors, Jonathan and Emilio. And I also want to thank some other people who were indirectly responsible and helped me out in this project. Sylvia and Jack for collecting and curating the data. Hans and Edong for looking over the paper before I send it out to Psychmethods. And finally, to Eduardo for helping me out with the continuous time latent change code while I was working on this project. And thank you to my wonderful audience. Thank you for listening, and please let me know if you have any questions.
Questions for Senior Gilbert?
Yes.
Senior West. Thank you. It was very nice. Thank you. I have a question. So one of the main things with accelerated longitudinal designs is that you have the issue that there are cohort effects that are intermingled with your time effect. And the trick seems to be a lot of times when people will resort to like a time and study coding and use the cohort, this kind of an cohort effect as an interaction to account for differences in the initial starting levels. If I was to do this approach, I would still kind of force everyone on the same trajectory because I will pretend or assume that that trajectory has they all started at the same place, which is exactly the thing that hurts in accelerated longitudinal designs because you are actually assuming that they do not start at the same place. How influential is the starting point? Is it just like a Bayesian or like a thing like you just get started here and figure it out, or is it like we start here and we stay here?
So the initial values are essentially the values at t equals 0. right? So if it is indeed the case that all the individuals have if their true trajectory follows very different initial values and are all over the place. So basically the heterogeneous condition in a simulation design, FDSD would struggle to do that. However, we are not forcing all the subjects to start from the exact same starting point, right? The observed data are allowed to spread out across the entire time span. So some individuals can start at t equals 0. Some individuals' first data point can be much later at t equals 15 or something like that. So we are not forcing every individual's observed data to be at the first time point.
But when you calculate, like, don't you end up calculating functional trajectories for every individual that span full time series?
Yes.
And so with that, the person who comes in very late has the functional form, the person who inherits whatever these 5% of your sample did down there. And so, and I wonder if it's just a matter of changing the time where you set this. But I would think in an accelerated functional designs, I would think that hurts because that is exactly the feature that I would expect where the largest, where these individuals differ the most.
So you might, that's possible, correct? If you're just observing a specific individual right towards the end of your time span of interest, we do not know what they're doing earlier in life. So we do have to assume that they are somehow following the others in some manner or the other. That's the same for CTLCS as well. It will not magically give you the initial value.
Yeah, and then that kind of, if you let's put it into quotation marks, criticism is the same as one could give to the model. But and so that's that's not the. I was more like curious if you gave this a thought.
If my general takeaway is that if the trajectory of that specific individual who you are studying much later in your time span of interest, if their trajectory is very different from the rest of your subjects, they will be forced to follow the trajectory that's the same as.
And you could select it at a different place too, right? I mean, you don't have to use the initial values. You could select it at any point in that trajectory, or can you go like backwards as well?
I did try that. It did not work as well, but I did not try it out that much. That might be something that to try it out with rigorous simulation, but I haven't really looked at. Yes.
Can I see your results for the heterogeneous position?
Do you want the tables or?
I want to see the box plots.
Yes.
I guess you've sort of already kind of talked about this, that like you think it has to do with like the metrics overfitting so it looks better. I guess I'm a little bit confused why, and I guess I'm asking you to speculate on this. Like why in this one the latent change score stuff would work better, just because the logic you provided for your third condition where it's like, oh, the FDA approach is like non-parametric, so obviously you have these differences and the non-parametric approach is gonna it's gonna work better. I feel like that should apply to this condition too, and I don't totally understand why it doesn't.
My intuition behind how this algorithm is working is that since it's totally non-parametric in nature, it has to learn the trajectory from the observed data of the subjects, right?
Mm-hmm.
So if they are really spread out over the time domain and the observed domain, it will essentially spread out all the simulated trajectories. And what that means is that if it's really spread out, the mean curve, the population curve will take into effect, and that will dominate the the subject-specific trajectory estimation. Whereas for CTLCS, since it essentially tries to fit to the observed data, there can be certain cases where it can drop down and fit very well to the observed data. So for that specific subject, so it actually works out for this example here. For this trajectory afterwards, the integral squared error will be very low, right? Because the area between the true trajectory and the estimated trajectory is just this. So just this portion earlier in the time span. Whereas for FDA SDE, since the entire trajectory gets moved up, you have this entire area that shows up.
Okay, that helps. Thank you.
Yeah, I have the same intuition that as you did, Daniel, especially because generally speaking, the parts that are more difficult to estimate in the latent change score model are the variances. So if you don't have variance in the data, it should be easier to accommodate everybody. But then I think the answer is WTF. What is the function? That's the answer. That's not my job, by the way. I'm just taking it from somebody else.
In the name of the paper.
Other questions for Sir?
So I had a question on this slide actually.
For understand, yeah.
Yeah. Well, so you were saying that it's a limitation that we are seeing these bubbles around the confidence interval when we don't have the data, but isn't that a good thing that the bubbles are there? And we should not be confident of the functional form because we don't have the data.
Yeah. For the cases that I have here, yes. There are many cases. So if you look at the this one, these go all the way up. Some of them, as I said, they exceed 10 raised to the power 5. And that seems like it goes from positive infinity to negative infinity. And I don't think that's very helpful, right?
Yeah.
Yes.
I had a question piggybacking on Rohit's for like I think it was the North study with the confidence intervals. So if, in my memory, the 2 right participants, that's not ideal. But even for the first one, similar to Rohit, is you do want the more uncertainty before you get the observations, but then it looks like for the FDA, it's like consistent uncertainty across the entire time span. So what, I don't know if it's necessarily a question, or more so just kind of echoing Rohit, wouldn't you want it to be wider uncertainty and kind of narrow off what you see observations? Wouldn't that be a desirable property?
Well, that depends on since these are not actually analytically derived confidence intervals. Remember, these are estimated using a bunch of simulated trajectories that are just defined by their initial values, right? So the initial values, if they are pretty close knit to each other and you start off the algorithm, they will take the shape of the entire trajectory, and you won't necessarily have the ballooning effect just because of how the algorithm performs, how the algorithm estimates these trajectories. You will only have those ballooning effects if for some reason the conditional mean and the conditional variance blows up. And that might not necessarily happen if you have decently closely packed observed data. You can have that if there's a lot of gap between 2 time points, between 2 time grids, and in those cases, you can see jumps and bigger confidence intervals. But my argument is that here it's more data driven, and that's problematic in and of itself, right? It's not totally analytically defined. So also our interpretation of these confidence intervals need to be different because again, these are not actually analytical confidence intervals.
Could you go to the figure for your functional heterogeneity condition?
Oh, yeah.
The selected subjects. Right. So when you're fitting the continuous time LCS, you are wrong for 50% of people, right? So technically you're not fitting the right model to anyone, but like you're more correct for 50% and you're wrong for the other 50%. Do you have any intuition for the FDA on how often it picked up that decay for people that decayed? Right. So like for the top row, at the very end of that trajectory, it's saying this person could stay the same or go down. I'm not sure.
Yeah.
But then for this bottom subject, it's pretty clear that there's this downward shape to this trajectory. Do you have any intuition if it did better than being 50% wrong?
I haven't looked at the clustering effects or anything of that. That'd be interesting to look at that. And decently straightforward to pick out the trajectories and look at that. But I have not looked at that. Would be interesting. Yeah.
Yes, I had a question on this slide. So the whole argument against LCS is that it's not able to pick up the functional trajectory when it's different than the exponential one, right? But we have seen in the examples you've shown that it does orient the trajectory when it's estimating it to be a little bit shifted. Like it can jump around in its estimated trajectory. So can an argument be made that if we were to observe one observation towards the end of that age in the cohort, like, can that help LCS to estimate it then? Because then it will have something to orient it and go towards it instead of relying on those three observations. So they make an argument that if we plan ALDs where one of them is spaced near, but the other one is very spaced apart, then we would be able to actually capture those trajectories. Because I know Eduardo has done some work where he has some longer distances between time points. And I wonder if you can have that as a condition to explore that LCS can do better. You just need to have more space in your time points. Yeah.
But that would be interesting. Yeah. That's possible.
When your Nora, one of your figures is 2 data points spread further apart.
Not more than 24 months.
I think it might have been heard.
Oh, the NGCS one?
Yeah, I might have thought that one has 2 much further apart.
Yeah.
And it is estimating
about the same as empty, right in the middle.
Yeah. Yeah. Awesome. I guess as an applied researcher, it might be more resource intensive to sort of wait 15 years for the kid to grow up.
Yeah, that's the whole point of it.
Well, it doesn't have to be too far apart, but
Yeah.
I wasn't saying too far apart, but from the simulation perspective, if you can explore that.
Sure.
Yeah.
So good.
Okay. Well, thank you, everybody. Thank you to everything. Next week, we have Greg Hancock from University of Maryland, who will be connecting with us via Zoom.
Yes.
Thank you.
Thank you.
Awesome.